The final topic of Chapter 6 is the normal approximation of the binomial distribution. Section 4 of this notebook, which corresponds to 6.5 of our textbook. Here's a summary. A binomial sum can be approximated by a normal distribution where the expected value mu is np and the standard deviation is square root of np1 minus p. The expected value is pretty much straightforward. For example, if you roll a die 600 times, you expect about 100 aces showing up because you get 600 times 1/6. That makes a lot of sense. Mu equals to np. Standard deviation, on the other hand, is not that simple. Square root of n, p1 minus p. For example, in the same example, that's square root of 600 times 1/6 times 5/6. Now for binomial average, well, divide everything by n. So what do we get? np divided by n, so we get mu equals to p for average. For standard deviation, we just divide by n from here, which is equivalent to dividing by n squared from the inside of the square root, eventually generating something like this. Let's go to an example. According to Federal Highway Administration's 2007 statistics, the percentage of female drivers has just surpassed the percentage of male drivers in the United States. 50.2% are females. Suppose that a random sample of 20 drivers is selected for a survey. A. Use the normal approximation to estimate the probability that less than half of the selected drivers are female. B. Use the binomial distribution to calculate the probability that less than half of the selected drivers are female. Let's do B first. This is something we did in Chapter 5. And here we go. And this is a probability that exactly k drivers are female. K success, 20 minus k failures. And that k goes for 0, 1, 2, all the way up to 9. The problem said less than half of the drivers are female, right? Out of 20, exactly half will be 10. Less than that, so we have to add up from 0 to 9. And calculated, we get 0.404 something. And, well, you can even draw the histogram for that. And, well, less than or equal to 9, we just include all those dark blue rectangles, and everything to the right, all those light brown, light blue rectangles, we just leave those all out. In any case, we get this probability, 0.404 something. That is the precise probability using binomial, but binomial computation is often a terrible thing to do. Well, even using computer algebra system, if this one goes up to 200, or instead of 20, go to 200 or 2000, we're going to run into trouble. But if you use normal approximation, no trouble whatsoever. By the way, there's one tricky deal about this normal, because what exactly do you mean by the difference between less than 10 versus less than or equal to 9? There's no difference whatsoever for binomial, because there's no such thing as 9.2 people or 9.7 people or something like that. But for normal, which is continuous random variable, we have to be very careful about that kind of thing. So less than 10, less than or equal to 9, for normal approximation, which is a continuous random variable, you have to take the midpoint, 9.5. You have to do something like this. Mu is 20 times 0.502, 10.04. That was easy. Sigma computation, that was easy too. The key is to get that. X is less than 9.5. Not 9, not 10. Right in the middle. Because this is a continuous random variable, you see. Okay. Let's do the computation. Let's draw the picture and do the computation. Here's a picture. And, okay, a little bit less than have, as you can see, and z-score computation, x minus mu over sigma, 9.5 minus 10.04 over the standard deviation. Calculated, we get z-score of negative 0.24 something. According to the precise computation with Mathematica, I got 0.40585, which is remarkably similar to the precise figure which I did with this binomial. This is normal approximation, very, very similar. Now, what if you use the z-table? Well, here we go. We get negative 0.24, negative 0.24, so this is the right column, negative 0.2, and 04 column, yes, 0.4052. So we get probability P is approximately equal to 0.4052. This is what I got from the normal table. And let's compare. And this is a little bit more accurate, and this one is approximation through normal table. Both are normal approximation. This is a little bit more accurate. This is a little bit less because we got it from normal table, which did rounding up to only 2 decimal digits of z-scores. And compare these values with this one, very similar, 0.4 or 0.4 or 4868, very, very similar. In short, the normal approximation works very well even for such a small n value, n equals to 20. Well, the reason it went so well is because the probability P was very close to 1/2. If it is really close to either 0 or 1, then the normal approximation will not work very well. You'll have to do something called Poisson approximation, but I decided not to cover it this semester. Okay, one final topic. What if you miss this 9.5 where this, in terms of binomial, less than or equal to 9 versus less than 10 are the same? So for continuous random variable, we take x equals 9.5. What if you just missed it? And then just use x is less than 9 or x is less than 10? Well, if you did that, then here are your computation. If you use x is less than 9, we get wildly different z-score, and then this kind of computation, 0.32 something. Less than 10, if you use that, then you get 0.49 something. And compare these values with what you got from, well, binomial. They're not similar at all. This one and that one, not similar at all. The reason? When you use normal approximation, make sure you get appropriate decimal, something 0.5. And how do you do that? Less than 10 and less than or equal to 9 are equivalent in terms of binomial, because binomial is discrete random variable that takes integer values only. If you approximate it with a continuous random variable, you have to take the average of these two and use 9.5. Doing that, you're going to get really, really accurate approximation. Just remember this 0.5 thingy and this binomial approximation, or excuse me, normal approximation of binomial distribution becomes suddenly easy.